you realize, of course, that I was only 10 years old when I did my first work on grid forming converters. Um, with that being said, let's get going. I think this has been a really exciting and interesting series. Thanks to Ben, Sairaj, Brian, everybody else in terms of pulling the UNIFI consortium together. Glad to have been able to kind of help. I think Duncan, you're right. The seminar is much about the presentations, which have been really exciting and very good, but also about the follow-on discussion. So encourage everybody out here to kind of be an active part of this. All right, so let's get going. Just kind of a second of advertisement for the center. So I lead the Center for Distributed Energy. I came here after running Verintech about in 2015 because we were seeing this whole issue of highly distributed and decentralized grid starting to become important. And we hadn't even begun to identify the right questions, forget the right answers. So I thought got my arm twisted to come back and we set up the Institute really to look holistically at how could you not only develop these solutions, but how could you rapidly get them to scale and get them to market. The fundamental focus has been digitalization, decentralization, and decarbonization. And many technologies have really come out from the center, and hopefully, we can continue to do that in the days ahead. Let's kind of see if we can spend a minute to frame the conversation out here. Clearly, everything here is being driven by some overarching goals. I mean, it's been really, hey, can we do something about the climate? And using, 20th century technologies, that's been a bit of a Faustian bargain. It's climate or economic growth, and that's not a very good choice, especially for emerging economies to have to make. What we want to do is kind of get towards a situation where you have economic growth, you have abundant, reliable and low-cost energy whenever and wherever it's needed. That's kind of the miracle that we're looking for. In addition, as we grapple with climate change, we really need to have improved resiliency at the grid edge. This transformation, is very difficult with technologies that we have been accustomed to. And we are looking at possibly at electrification as being a mechanism to really, make this happen. We are looking at 21st century technologies that have very steep learning rates. This may be a chance to kind of regain the global lead as far as the US is concerned. So, I mean, this is not news. I mean, we've been looking and living with this for many years now. In fact, I mean, at the EPRI summer meeting, which was just concluded a few weeks back, they clearly defined the target to 50% carbon emissions by 2030 and down to 0% by 2050. A lot of shaking heads in the audience. I mean, virtual audience, of course, but is this achievable, and what will the cost for this be? Yet, I think everybody is kind of getting ready to do this in some form or the other. And what we know best is it's a centrally planned and controlled system. We have kind of integrated resource planning. We have detailed system visibility. We have optimization. Things that we have really got done very well over the last little bit. And this has been all good, but we are being kind of confronted with things like solar cell costs and wind costs that have been dropping dramatically and systematically for, in this case, 50 years. We are looking at microreactors coming out. We are looking at storage coming out, hydrogen coming out. There's so much of confusion, going on. There's so much noise out there. How do you know what's going to happen? And yet, I think we are all trying to tackle it. We have a very complex utility, electrical system that is running today. It's been honed over 100 years of operating. And we are trying to make sure we get ready for that, essentially to accommodate, all the changes that we think are coming. The idea is you build, a better generation, more transmission, better visibility, better control at the grid edge, put storage in, build HVDC, build FACTS. These are solutions all that we have. The question is, can this really be scaled reasonably? I had the good fortune to be on a recent National Academies Committee on the future of electric power in the US, which was released earlier in the year. I have to say this is my personal opinion, even though I was a committee member and helped write parts of the report. What we acknowledged and what we saw was the system is on the cusp of fundamental transformation. If you look at all the predictions that have been made in terms of what the system is going to do over the last 20, 25 years, we have been spectacularly wrong and continue to be spectacularly wrong. And so, it is difficult to make forecasts about the future. And what we saw was that these drivers of future change were all there in many, many ways, but the ability to predict was poor. So how do you cope with that? When you can't predict properly, how do you cope with that? Some things we, kind of saw, which are kind of interesting. Yes, we need low carbon generation, but with high dispatchability. That's a problem. We need lots of storage, not only multi-hour, but also seasonal time shifting. How do you do that? We need modular distributed edge intelligent paradigm that is now beginning to compete with the existing grid. How do you manage that? Yes, we do need new techniques to ensure coordination between inverters. And that's fundamentally what UNIFI is about. So we were really, present in terms of being able to kind of, identify that. Reliability and resiliency at the edge is really where it's important. I think there's a new paradigm that can be implemented out there. Distributed generation is being deployed at the grid edge, represents a vast untapped resource. But regulations don't really allow us to use that very effectively. So a whole bunch of things that continue to be indicative of the fact that fundamental change is occurring, and is the utility industry, the electricity system, ready for it. I try to boil this down in this one slide. So lower left quarter, we see that, yes, we have a planned grid operating paradigm. We have 100 years of experience running very large complex systems. And we have the systems that are really kind of at the heart of it. The challenge is this the path that can scale? And, I think the conclusion that the committee had come to, and I think I'm agreeing with that, is that many of these changes today are occurring outside of utility control. I mean, typically utilities have been able to move systematically with proper resource planning, with kind of long-term horizons in terms of investments that are being made, and they control the rate at which technology is introduced so that the risk is maintained fairly low. What we are seeing now is we're seeing increased DER penetration at the grid edge. We're seeing prices dropping precipitously for PV, wind, and storage. And the question is, how do we coordinate these inverter-based resources? It becomes the challenge, and we are definitely addressing that in UNIFI. We are seeing an electrification of everything, whether it's driven by decarbonization, or really in the case of electric vehicles, it's driven by pure balance sheet as far as both the manufacturers and the operators are concerned. And especially for fleets. And we see a very fast, sustained year-over-year growth occurring. And if we start translating that into fast charging requirements, you might have to double the peak generation capacity of the US in the next 20 years. This was just, I think, reiterated by Elon Musk a few weeks back. How the hell do you manage to do that? And that's happening outside of utility control as well. And then resiliency is the other issue that we starting to grapple with, whether it's hurricanes or fires or cold snaps or cyber physical attacks. And again, the response out there is not fully under utility control. And that raises kind of a very fundamental problem in how do you kind of prepare the system to deal with all the changes is happening. When you have unpredictable things happening, you need to be flexible and adaptive and move very, very fast. And these are things that the utility system today is struggles to do. The other thing, clearly we have a much more complex system, even more complex than what we have right now, emerging. Okay, because you have millions of people or devices at the edge that are going to be prosumers, or some are owned by utilities and some are owned by private individuals. You have inverters made in multiple countries, some that are not necessarily friendly to the US. This becomes a real challenge in terms of ensuring communication and everything else. Communication technologies are changing, every few years as well. How do you make sure that all this is happening properly? So this becomes a very fundamental issue, as well. And what we see is that when we start scaling this, we start seeing a lot of challenges beginning to emerge. We've been talking about, DERMS and ADMS and aggregators and how, the market functions are going to happen. But at the same time, we have multiple things that we have to do. We have millions of inverter-based resources that have to be coordinated. Cybersecurity becomes a very big challenge when we start doing that. But at the same time, the real-time grid must run. If your communication is held up because of a cyber threat, you still have to make sure that the system will continue to operate. Again, for the UNIFI crew, this is not all news, because this is a part of the premise. But how does the utility communicate back? I know utilities today, big ones that have 6 to 7 completely independent communication networks, each of which is obsolete and each of which has to be maintained. That's a really problematic way in which to be able to maintain this and do this. So we can see that just from a scaling perspective, whether it's IT layer, whether it's cyber layer, whether it is the number of resources, whether it's regulatory issues, in every aspect, this is a very, very complex problem. And to compound the problem, everything is moving at supersonic speed. Somehow we had to magically figure everything out on the move without letting the lights go out even for 1 minute. So, my utility friends, I have a lot of them. I feel the pain, and hopefully we can kind of come up with answers that make sense. So at the heart of this is the grid, where the control is now going to go from passive generator-based, inertia-based kind of control with things that happen automatically at high speed, and everything else is kind of coordinated from a market perspective. Protection, of course, operates autonomously as well. But inverters are going to be the main mechanism for control. Less so immediately, but more so in the future, and it's going to morph at speeds that we really cannot fully predict, and yet we need to develop a system that will work out there. So we see a lot of power electronics coming on the grid. And as Duncan said, I've been working in both of these fields for a very long time, and fortunate to have been able to do that. But we see that power electronics is coming at every scale, right? HVDC was there for quite a while already. Then we started to see emergence of voltage source converters, and they can do a lot more in terms of systems. We're starting to see multi-terminal DC grids. We're starting to see HVDC circuit breakers. So there's a lot of technology development going on that allows for large systems to be built, which can influence power flows in the grid and at bulk levels. We also see distributed solutions now starting to become really, prevalent as well. And whether they're like the smart wires that we help to develop, or it's storage or inverters for PV and wind. I think we've seen in Tesla in Texas as well as in Australia, they were able to build 100+ megawatt systems in a matter of weeks. This kind of speed of response is very, very difficult, normally for bulk power installations. So that's one thing that starts looking very interesting. And then at the grid edge itself, the fact that we have rooftop solar, we have microgrids starting to come up, we have resiliency issues. So we are starting to see a proliferation of inverters at a pace that we just could not have imagined. The problem, of course, is do we understand what exactly is going to happen as we get to high IBR penetration? And I would like to suggest that this is a problem that is far from solved at this point in time. The graphs out here from a thesis from Leuven, but there's many other documents that kind of show this. This shows you a very simple system where as the network changes, the impedances and the resonance points change quite dramatically, and you don't know which one you're going to have. So that system knowledge is problematic. How do you ensure stability? How do you, what kind of interactions are you likely to have? What is the network topology, and what are the cyber threats that you're going to see? How do you ensure interoperability when you have so many different vendors? Can I build something that's plug and play? I mean, what do I do with a standard that is 6 years old and is likely to go and get changed the next 2 years? How do I design product around that? Can I build this, to have autonomous control? So this is, areas that we are all quite familiar with. How do you tackle this? And we kind of at the center decided that the way to think about this was, let me try to begin to decouple and create clean partitions. And one thing we wanted to do was, can we build an inverter that is high performance enough that it can decouple the interaction with the rest of the system and provide a scalable building block? And if we can do that, then we have an opportunity to be able to, develop higher level controls that will be interoperable across different types of systems. So, just a quick deep dive into, one of the converters that we have developed that looks very, very promising at this point in time. We call it a multi-port bidirectional universal converter, and it's based on a topology we have patented and published. It's called the S4T, a soft switching solid state transformer. Really interesting because it's very, very flexible. And it's completely bidirectional, does AC, DC, whatever you want, has 0 voltage switching on every terminal so that you can switch at pretty high frequency and get very high control bandwidth coming out of it. That performance allows you essentially, the fact that it's a current source has essentially capacitive filters on the output, allows you to parallel and scale this in a much easier way than would otherwise be possible with voltage source inverters. Of course, this requires reverse blocking devices, which are not available, as all those of you who work in power electronics would know. So we've worked with multiple vendors to actually build custom power modules that have reverse blocking, fast switching devices embedded in it. And we've been able to kind of take that up and show very high performance. This technology is now getting ready to go to market. You can look at gridblock.com if somebody is really interested. And we've evolved this into a 500 kVA S40 building block, which connects directly to medium voltage on the other side. You can now parallel it. So, what kind of applications could you think about for this? PV and wind farms, energy storage, DC fast charging. These are all very, very rapidly growing sectors where you need to have some, high control or high performance, capability at the edge that allows you to do all this multifunction, things that we've been talking about. So this is one of the things. The other thing you can do is look at, for instance, microgrids, whether it's at the resiliency point, whether it's campus and utility microgrids, or it's flexible energy access type of microgrids. So there's a need, we think, for a low-cost, flexible, scalable device that can be used to implement various of these, these various functionalities that we've been talking about out here. We've also been able to take that and extend that out to medium voltage connection. We've done multiple projects with DOE where we've demonstrated a 7.2 kV, 50 kV solid state transformer. What's interesting is, the functionality has been shown by many teams before, but you need to really, for this to be practical, you need to be able to meet all the stringent requirements. Protection, mainly 90 kV BIL, short circuit. I mean, these are all things that are, going to shape whether these inverters and converters can work or not. I don't think medium voltage inverters are ready. I think technically we can show they're feasible, but from a cost point of view, I think we have a few years to go. Will they come? Yeah, probably they will, and hopefully we'll have a role to play there. But to have high frequency transformers with high voltage, high kV BIL, and to have a converter itself be able to survive 90 kV BIL was extremely challenging. I think we've been able to demonstrate that. All right, so we have a high performance inverter and an engine, and I can, work magic with it, but can I manage 1 million of them? Sometimes there may be only one, and sometimes there may be 100, sometimes there may be 1 million. How do you manage something that is this level of complexity, and it's really very challenging in my mind. We grew up as engineers, and we were taught that the best way to do this was to model, analyze, simulate, and manage these large systems, right? But today, if you look at it, I mean, the best controllers are all adaptive nonlinear controllers. When I design an inverter, I mean, yes, I declare a lot of things, but I have so many hidden protection layers because I don't want that thing to blow up out there when it's in the customer's location, right? To make it flexible, I'm giving, over there software updates. So how do I model all this? And then on top of that, this thing is moving at, 2-year, technology cycles. Okay, so what do we really want? At the end of the day, we say, okay, we are spending billions of dollars developing autonomous cars. Why can't we start with autonomous inverters? Okay, which just connect to the grid and it works, right? It sounds aspirational and sounds a little technically very challenging. But let's kind of flesh out what this really means, right? So we're going to have a situation where you have geo-dispersed inverters, that you just want to connect to the grid. Oh, but you're going to have communications latencies. In that kind of situation, you don't have very good system knowledge because these are all ad hoc things that are happening around you. The inverter has to be operating based on local measurements. And it doesn't really know what conditions it's operating on. Is it normal? Is it transient? Is fault? Is startup? Is connect? Is disconnect? And the inverter needs to figure it all out and keep running. The same controller should work whether it's grid connected at the bulk system level or the grid edge level, or it's a microgrid mode in island situation, because again, the inverter may not know what the current configuration is. Okay, and you may not be able to rely on communication because of the latencies and because of cyber issues. So this is again part of, this has driven our thinking for 30 years now, and it's just gotten more and more emphasized, right? So what does local control do? The lowmost control really should suppress undesired interaction with other grid elements, right? Whether it's other inverters or it's other transformers or it's capacitors, and just kind of make sure that those things are not a problem. And that's in a real environment, where you have latencies, you have sensor control bandwidth, noise, inaccurate knowledge, all of these things are real things, and you need to be able to operate with all of that. And then at the end of the day, you have to be able to operate with an unknown number of devices that may be similar and compliant, or maybe dissimilar because they were older generation of technology or somebody who didn't care, right? And you need to be able to manage that and then still be able to operate automatically in conditions where sometimes you have a surplus and sometimes, because we have so far operated in a system where generation follows load, but when the generation is not fully dispatchable, then sometimes load has to follow generation. Okay, and now the question is, what does this all mean? I mean, I always believe that, what does the system look like? Ultimately, if we can begin to define what the system looks like, maybe we can get there. I always say that if you don't know where we're going, how do we actually end up getting there? So I would kind of propose, and maybe this is part of what Duncan was saying, that let's make it controversial, right? But let's figure out what we're trying to do out here, right? So we are talking about a centralized control of a future grid where you have a varying mix of generators and intelligent inverter-based resources, and with high complexity because you have communications latency, you have cybersecurity issues. How do you kind of figure out how this thing is going to operate? Our feeling is that let's talk about this idea of collaborative control. Where we have these intelligent, grid edge devices, right, that use local measurements and follow standard rules. Okay, they act in real time and they fulfill individual goals, and then they collaborate to sustain the grid. This sounds kind of outrageous. I mean, this is not the way we design systems, but there's a lot of examples of what you would do where this operates. I mean, the one that's always appealing to me is the one on the lower left. If you look at a tandem bike, you have 2, 3, maybe more people who are sharing a mission of keeping the bike vertical and moving at roughly a standard speed. And they're sharing torque essentially with no communication except through what they feel within their, from their feet. So there's a mechanism of collaboration out here where the speed is roughly important, not exactly important. Torque control, power control are in dynamic real time, that sounds very interesting to me. The second one that kind of is amazing for me is, if you look at just driving in traffic, you can have a 1921 car in parallel with a 2021 car, and they share the road, and sometimes it takes you a little longer to get to work, and sometimes you sit in a traffic jam. But by and large, you are able to get to get the objectives of the system as well as the individual accomplished. And it only happens because you have the intelligent edge agent, the driver, in there. And I think this is kind of at least gave me an example of how to think about this problem. We did this at Verintech, where we were. I think we had the first completely decentralized volt-var control system, where we were deploying essentially as many. On this chart you see on the right, we had, I think, 94 VAR controllers all working together based on local measurements. And using this collaborative technique to be able to stabilize the voltages across the entire feeder. So here, what we need now is inverters that act in real time without detailed system knowledge. I mean, without even knowing if they're grid forming or grid following. So when somebody says, you're building a grid forming inverter, I said, yes, my inverter can form the grid, but right now, does it need to form the grid? And I don't even want to put it in different modes, because I don't know if that mode is important, or if it's a very stiff grid or a weak. I don't know any of that, right? So I wanted to figure it out all automatically. So our feeling is that what we really need is a fundamentally different paradigm out here, right? Where today we think of the grid as a resource. But when everybody in the system is going to act to sustain the system, okay, then it's an ecosystem, okay, and we all need to act to sustain it. And yes, of course, once it's sustained, then you can actually use it. Well, this is all great. This is all aspirational, and this could have been a social sciences class or something. But how do I translate these very high-level objectives into a technical specification? That becomes, I think, interesting. So I'm going to take you guys through an example of what we did out here. This has just been published at ECC 2021. Shout out to Mohammed Miran Begi and Prasad Kandula, who worked with who really worked on this. I'm just reporting the results out here, but it's an example, and I think what we are trying to do is get back to fundamentals in terms of how we think about the problems. I think we may even have better ways of doing this right now, but this gives you a very clear example of how we think about this. So let me kind of throw something else out there. I've designed a lot of inverters. I'm sure many of you out here have, and others are design other devices. And we typically design these devices to prioritize our own goals, because we're paying for it. And if they happen to sit in a multi-device system, then any interactions are almost secondary unless there's an emergency of some kind. And to be able to assess what that impact is going to be, we really want to see detailed controller and system models, and to be able to work with those to see whether the system is going to be stable or not. And then, of course, we run into problems because the vendors want to keep their control algorithms proprietary, and so then we're struggling with this, and this is a problem that I think everybody's aware of at this point in time. So I would like to suggest that there's a slightly different way of thinking about this. Okay, so let's look at this new inverter control priorities. I suggest that we have to design these so that the support of the grid as an ecosystem is priority number 1. Priority number 2 is you suppress interactions, and then priority number 3 is you meet local needs. So it's a flip of the way you think about the problem. And that's important because, if the grid is not a resource and all of you stop supporting it because there's a fault on the system, okay, all of a sudden the ecosystem goes away and you don't have a source available at all. Okay, so it really flips. And if 99% of the time, everything is working, then your local needs are met. So this is, I think, a much better way of doing it. Also, the other thing we think is that, because you have a certain amount of control effort available, instead of a layered approach, we think it's a much flatter priority shifting control with as much of feed forward as possible and very slow feedback loops to try to stabilize the loops. That seems to work, in my mind, a lot more, a lot better. And you want to be able to do all the things that need to be done to kind of make this thing work, whether it's voltage and current control, impedance control, angle control. I have a problem with frequency control a little bit, because when I have fast changing frequencies, I don't really know what that frequency is, and then inertia and damping is as well. So we developed this universal controller concept, okay, where you can just simply take the inverter and connect it to the grid over a pretty wide range of realistic conditions, and expect that it will, automatically operate. Doesn't matter if it's islanded mode or it's, in grid connected mode. If it's grid forming or grid following, all is exactly the same, control in terms of how it's done. Communications is working or not working, doesn't really matter. And then it uses communications mainly for optimization and for market functions. The whole idea is, if you connect them together, it's going to be in the steady state, and then yes, you have PF and Q as the fundamental parameters that get controlled. We like to think of point on wave because things are really kind of happening dynamically out there. And we think of frequency as being a transactive parameter, because in the steady state, it's really what everybody's kind of zeroing in on. We think that because it's part of the ecosystem, it needs to, provide inertia as needed. I don't know if it's high, if it's low, whatever the need is at the moment, because I have an intelligent, fast responding device, I need to provide inertia as much as needed. Yes, of course, watts and vars, and it needs to, damp oscillations and resonances, needs to suppress interactions with other inverters and generators. And yes, it needs to manage large phase jumps. It's that stuff happens, right? To be polite. And when it happens, you can't say, hey, I give up at this point in time and go into protection mode. You're part of the ecosystem. You do as much as you can to keep everything running. You need to be able to do a bottom-up black start. You want to be able to form resilient and fractal microgrids that separate out and keep operating and connect together as conditions become good. So aspirational, but I mean, this is part of what has been driving the way we think about these issues. Other issues that are not covered in this controller right now that we have really been focused on quite a bit is, in a IBR-rich system, you can go, wildly from energy surplus to scarcity, and how do you manage to keep the system operating? What is the transactive control mechanism when you have, different owners for different inverters? How do you develop vendor agnostic controls? And how do you think about cyber resilience in a situation like this where you have so many inverters out there? So let me give you some very quick results on it. This is an ongoing set of projects and publications. This one is just released, so I can share this with you. This shows you a simple system with 2 microgrid connections, back to the grid, and it shows a pretty large, a long list of long cycle of continuous events that happen, which the inverter controllers don't really have any knowledge of. So we take this, start the microgrids up, interconnect them together, interconnect them to the grid, put a fault on the system, and in the process we see a number of different things out here. So we see that there's an adaptive current limit that acts when there's a system fault or a phase jump. And again, I think, as I said, I think we are going to change how this is done, but this is a good kind of implementation of functionality that has been very challenging to do. So what this does is eliminates the need for synchronization. Inverters can seamlessly connect to the grid without any system knowledge. And I can, the other thing we do, which is really quite interesting, is when you think about inertia, if I take a microgrid that is functioning, it's a distributed microgrid. So inverters don't really know where the system voltage is. And I connect a switch that now creates a phase jump for this microgrid. Okay, what do you do? So inverters typically operate trying to present a high inertia on the system so that they are, they're suppressing any dynamics and things that are happening. And then when you end up getting a situation where the inverters are near the edge of their control, okay, then the inertia automatically goes low and allows that inverter to do a phase jump and stabilize the system as quickly as possible in that new position. It operates automatically in dispatch mode or droop mode and achieves PQ sharing under steady state conditions, which are all desirable properties. So again, not to say that this is the only way to do it, but if we can do this, then I'm sure collectively we can do a lot better. We have validated the simulation in hardware in the loop as well as in hardware, and we're now building a larger test system as well. So this is an example of how you would build grid forming inverters and actually try to achieve the functionality that we think is meaningful for being able to build systems with widely varying range of generation to inverter control. One more thing that just quickly want to go through. This is a paper. This is actually a PhD thesis for Rohit Jinsivale. He's now with PNNL. And he did some interesting work on integrating real-time physical and transactive control. And what we did was, because we had to ultimately close the transactive loop, and we wanted to do that without that communication being there. And we kind of created a price to frequency mapping on the droop characteristic, and use that essentially to inform the agents in terms of what the real-time pricing is, and allowed loads and sources to all dynamically respond to that. He did some really good work in terms of developing the simulation platforms for that, and being able to look at how you would handle contingencies like congestion and other things, and what kind of controls would be required. But this, he did a simulation with, many hundred, 500, 450 plus consumers, all with different preferences, and saw that you could get the system to stabilize. And interestingly enough, I mean, this operation is exactly equal to autonomous economic dispatch, and that was, I think, a very interesting outcome as well. The answer that we always see, want to see in terms of how will we get all these converters from different manufacturers to get to the same point, we always rely on standards. And standards have been kind of around for a long time. I mean, my PhD work was based on IEEE 519, so that was 1981. So that goes back a long way. And standards are used extensively, and we, when they work very well. But they also presume, kind of a slower evolution of technology. I mean, if you look at 1547 itself, I mean, it started in 1999. And it was many years before it was released, the first one in 2003, and then many years after that before products became available that were complying. And then 2018 was the first major upgrade, and as we know that this is really still silent on things like grid forming technologies. So there is a time lag in the standards process, and we need to kind of recognize that becomes problematic when you have exponential growth and fast technology cycles, because we're seeing almost a doubling of installed megawatts of generation every 1.5 years roughly. Okay, and the standard cycle is a lot longer than that, and therein becomes the problem. We've talked about the fact that we need a forward-looking collaborative process to realize the rules and protocols that give us the flexibility and interoperability. And I think UNIFI can go a really long way towards doing that. I mean, I've always raised the the idea that organizations like the Bluetooth Consortium have had to deal with even faster technology cycles, and now have I think 9,000 or 10,000 organizations that belong and coordinate standards across the world and keep it moving. So there needs to be some way of kind of getting to rules, and then as the technology migration slows down, this will turn into standards, but there needs to be a mechanism by which we can actually understand how to do this in fast moving environments. So we've covered a lot of ground out here actually, and I'm hoping that I didn't lose you guys out there, but I want to kind of take a couple of slides and kind of begin to summarize some of this, right? So I think there's a transformation that's underway, right? We're going from grid as a resource to grid as an ecosystem. The problem is that we have really no way of knowing exactly how it's going to play out and exactly how it's going to evolve. There's a tremendous amount of uncertainty, and there's a tremendous amount of disruption that is going on. When you think about the fact that the electricity industry has, in the US, has almost $2 trillion of depreciated assets, it almost, when we've been in this committee meetings talking with the CEOs, it's very hard for them to see how you can take new technologies and replace what they're doing with it. And I think this comes really from two things. One is operational costs are low for renewables, and the costs are dropping dramatically. And we've seen the outcomes that they're now lower cost than natural gas and coal. And utilities are being pushed to really adopt those very, very quickly. So we have uncertainty, uncertain outcomes, but you have a very limited amount of time to do this. So what are the rules for the future grid? I mean, if we look at the left, I mean, this is a picture that we've seen many times now in UNIFI. I love the picture. It's the 1904 meeting in St. Louis, where we decided that we needed rules for the present, for the present grid. If you look at, I like to look at attributes. The lower chart, lower left chart, shows you the current grid and the future grid, and it almost looks like opposites. Centralized large assets, decentralized distributed, planned schedule, ad hoc variable coordinate. This is really very difficult for a whole industry to make that transformation without a lot of pain. And in some sense, I mean, I almost look at that thing on the right and I'd say that, is that an Amazon or somebody like that? But I mean, we have to make the transition because it's coming. It's, this is a freight train that's coming. So we see, rapid change and uncertainty. What is needed to tackle that? I mean, first thing is you create alignment. We need high-level technology agnostic objectives and impact metrics that we all agree upon. Okay. The problem is we don't know what we don't know. I mean, we're all experts. We've all been experts in our area for a very long time. And yet, as transformation occurs, even the experts, in the mature industries really, cannot grasp completely what that transformation is going to feel like and look like. And the VCs know this well, and this is an area that we see a lot of, right? Solutions, because that uncertainty really should be flexible, should be plug and play modular, so they can be put together. As technologies move, they need to be able to maintain interoperability, and that's the one way you can get to scale fairly quickly. And of course, the way to do that is through sustainable technologies that have high learning rate. In every other case I know, where disruption is being driven, it's being driven by the companies that are causing that change. And they have to have deep technology skills to be able to drive that. Here we have a disconnect between vendors and the utilities, and there's regulators on top of that. This is more challenging. Not that it cannot be done, but it's more challenging in my mind, at least. Tremendous research capabilities there in the US and elsewhere. And yet, to get to impact in a timescale that is this 30-year timescale, 25, 30-year timescale, needs T2M techniques that are not very well developed, and we really don't know how to accelerate this from innovation to impact. Big companies, have huge investments. It's very difficult for them to disrupt their own businesses. So in many ways, it's really the entrepreneurs who are going to do that. And yet, as entrepreneurs, and I speak from deep experience, in the space, death by pilot is a very, very common thing, and long adoption cycles. Look at smart wires. It's taken us almost 20 years to get from first, prototype to where this is now being adopted. And that's very long for VCs to wait and for investment capital to be patient for. So there's the fundamental, problem out there. And we can see that, hey, we will make this transition, except that because we are already supplying the utility industry, is already supplying electricity to people, every hiccup along the way is going to make it even more challenging, and sometimes it might even reverse the process. So I'm very, very concerned about that part of it. So, big challenges ahead of us as an industry. Before I put my last concluding slide, I'm going to do one more pitch, if you guys will excuse me. Um, I also lead this global competition called IEEE Empower a Billion Lives. It's come out of the IEEE Power Electronics Society, and it addresses this fundamental challenge of energy access. And by the way, energy access and what we are doing in UNIFI are integrally linked to each other. Because if we can make that cost low, then we can solve the energy access problem for the billion people who live off grid today. This needs new technology. And what they need is not just, don't need energy, but they need the livelihood and the services that come from it. So we launched EBL1 and was completed in 2019. We had 450 teams from 70 countries that kind of, registered for that. We gave out more than $500,000 in prizes. We're now launching EBL2. We have a 3-page concept paper that is due by November 30th. Student teams are welcome. We hope that every university will have a student team that will participate. But please look at empowerabillionlives.org and get ready to participate. We are looking for sponsors and teams. This is a great event. Excuse my pitch on this, but I hope we'll see a lot of you, out there as well. So to conclude, before we get into what I'm sure will be an even more interesting discussion process, we see that the industry is moving at tremendous pace and has a commitment to getting to zero carbon emissions. But it's very difficult to understand how rapid movement in many adjacent areas and a heavy emphasis towards decentralization, how will it affect the traditional utility paradigm? And I think we are struggling with managing this complexity that is coming out of it. And because we have this charge of keeping the lights on at the same time, okay, this is going to be even more challenging. It's my feeling that the only way to do this reasonably is with these exponential technologies, which are evolving very rapidly with steep learning curves that align with the societal objectives in terms of growth, sustainability, and equity. Okay, but this will pose a challenge for the transition path. We know where we're going now, but the path from here to there, can have a lot of bumps and hiccups along the way. And we saw what hiccups do for the system. If you were paying attention in Texas earlier in the year, you saw that very, very closely. We think that these solutions need to be more flexible, need to be more decentralized, more modular, interoperable across vendors, allow rapid scaling and technology migration, very aspirational. But I mean, if you set that as design objectives, and I think UNIFI is starting to do some of that, I think it's, I think it's very, very doable. And this is really not about just technology development, but it's really about the community. And Ben and I and Sairaj have had this conversation, many times, where we think that it's really, UNIFI will develop some amazing technology, I'm sure, but the objective is really to create that alignment and to create a process by which competitors can enhance and expand the market available for everybody and can do something that will come up with a solution that is good for society as well. And I do think that UNIFI offers a once-in-a-lifetime opportunity. This will not come again. We are at a very unique point on this trajectory where it's going to be still painful, but at least it's doable. In 5 years or 10 years, it may not be doable at all, and this can fundamentally change the energy system. And if we do it right, we'll have a flexible architecture and collaboration process that will emerge. Just a last point, major EV manufacturer, the most major one. There was an interesting comment, after a seminar at Georgia Tech, I asked him the question, said, what happens? I mean, you guys are talking about growth occurring and things are going to happen, and utilities are struggling to keep up with it. What happens when an irresistible force, meets an immovable object? And he says, we just go around it. So, I think there was another question like this was raised in one of the previous talks. I mean, are we, seeing desertion from utilities? I don't think it's going to be that, but, if we can't move fast enough, people are going to evolve solutions because the payoff is really very, very big. So with that, Duncan, I'm going to, stop sharing and we can go on to questions. By the way, if somebody needs to send me an email or a question, my email address is bdivan@gatech.edu. So